Hello viewers, welcome to our online lecture. I am Dr. Archana Choubey, faculty from the Department of Science. In the earlier lectures, we have discussed the theory and instrumentation of UV-Visible Spectroscopy. We have seen how using UV-Visible Spectroscopy, we can calculate conjugation in the organic molecules. Today, we will be dealing with another important topic related to UV spectroscopy. So, let us begin. Our topic for today is Woodward-Fieser Rule for calculating lambda max in dienes and polyenes. In 1945, Robert Burns Woodward gave certain rules to calculate the lambda max value of molecular structures. In 1959, Louis Frederick Fisher, he modified these rules, and by his experimental data, he gave certain more values to make the rules more useful. Therefore, combining the two, we study the Woodward-Fieser rules. These rules help us in predicting and calculating the maximum wavelength, or which we call as the lambda max, for any given structure of an organic molecule. We add certain contributions which are given in tabulated form calculated by these scientists, and using these values we can predict mathematically that what will be the maximum wavelength at which a particular molecule will show absorption. So, here as we can see that as the topic is about dienes and polyenes. So, if I am talking about a diene means a molecule in which there is at least two bonds, two conjugated double bonds. And if I talk about a diene, the smallest diene that is possible is 1,3-butadiene. So, taking that as the base molecule for any of these structures, and going ahead we can calculate for n number of such structures. So, therefore, dienes and higher molecules or polyenes, these they have certain fixed values of absorption where we can see and identify the presence of these molecules. So, first during calculation there is a parent value or a base value which we have to identify. As we do any construction, there has to be a base on which you keep on adding certain things. Similarly, for a given structural layout of a diene or a polyene, the Woodward and Fieser, they have given certain fixed values. When we are talking about diene or polyenes, especially in case of dienes, the dienes can be of two types. They can be straight chain or acyclic dienes, or they can be cyclic structures. If I am talking about a acyclic diene, then for these acyclic dienes, the fixed value is 214 nanometers. All these values which are referred in the table are in the unit of nanometers. So, for acyclic dienes, the base value or the parent value that will be taken is 214. Similarly, in case of a cyclic structure, there are two categories, homoannular and heteroannular. So, let us see what is the difference between the two. Here, as you can see, I earlier said that 1,3-butadiene, this structure that you can see over here, this is the smallest diene, 1,3-butadiene, because it has alternate single and double bond. So, when we are predicting the lambda max, we try to identify the presence of such a structure in the molecule, and for this we take the base value as 214 nanometers. So, in case of acyclic or straight chain compound, it is easy and the base value will always remain as 214. But when I am talking about cyclic structures, here you can see there are two different conditions that may arise. A cyclic structure in which the alternate single and double bond making 1,3-butadiene, a double, single and double. That means this is the formation of 1,3-butadiene, that is the parent molecule which we are trying to identify. It is formed within one ring itself, whereas when I take the other example over here, this is one condition where 1,3-butadiene molecule can be formed, and others can also be formed in taking the ring upwards. This can also be a 1,3-butadiene, which I am referring as 1, and other one which I am referring as 2. So, there are two positions from where I can locate the presence of 1,3-butadiene. So, the first structure where both the double bonds are present in the same ring are known as homoannular. Homo means whenever there is something within the same species, we term it as homo. So, it is homoannular ring. That means the conjugated base value which we are trying to find, it is within the same ring. And in the second structure, I have marked two places. This one which looks like homoannular, and the second where we are trying to identify the conjugation in the molecule. It is obtained in two different units by taking the two rings A and B together. So, such a condition in which the base value will be identified by taking the two rings together is termed as homoannular ring structure. So, going back, now let us come back to the initial slide where we have seen the various values. As we know that when we are talking about cyclic structures, in the base value for heteroannular diene will be taken as 214 nanometers, and that of homoannular structure, it will be taken as 253 nanometers. Now, apart from this base value, there are certain additions that we are supposed to make, or increments. What do we mean by increments? Increments means that apart from this basic structure of 1,3-butadiene that we are trying to search in the molecule, is there something extra? Is there any extra conjugated bond? Some extra functional group attached to it? For each of these conditions, there are certain fixed additions or increments that we keep on doing to the base value. So, if there is a third or a fourth bond in conjugation, then for each such bond a plus 30 is added to the base value. Similarly, if there is an alkyl substitution or a ring residue. What do we mean by alkyl substitution or a ring residue? Let us see over here. Alkyl substitute means a presence of an alkyl group. Like if I make this structure over here and I am talking about the presence of the basic molecule 1,3-butadiene. So, over here 1,3-butadiene is identified in these 4 carbons, and each of the carbon, this place refers to hydrogen. But if I talk about 1, 2, 3 and the 4th carbon, in the 4th carbon, if here is hydrogen, then this place instead of hydrogen it is a CH3 group. So, the 4th carbon does not have a hydrogen. If it would have been 1,3-butadiene, the simple molecule, then this would have been a hydrogen atom. But instead of a hydrogen atom, it is a CH3 group or an alkyl group. So, this is actually your alkyl substitution. This is your alkyl substitution which is present at carbon number 4. Understanding? Now, coming to, we have also used a term as ring residue. What do we mean by residue? Residue means something which is left over afterwards. So, if I am talking about the cyclic structures have ring, and if I break the ring or I imagine that I cut the ring at certain position, so it's like in this place, this is the 1,3-butadiene present over here, and each of these line is representing the presence of an alkyl group over here, here. If it is not H, that if R is written, that means it is also an alkyl substitute. And if I go beyond and I imagine that the ring is broken from here, so what is this position referring? It is referring to a carbon. Then this end over here, this is also referring to a carbon. So, the position that I mark as A and the position that I mark as B, these two positions are the part of the ring or the ring residue, and they are equivalent to an alkyl group only. An alkyl group is any free alkyl group, it can be C2H5, CH3, whatever, but this is a carbon atom which is attached to the ring, but it is not part of the conjugation. It is present along the conjugation, but it is not directly a part of it. So, each such position will be counted as ring residue when you are talking about cyclic structures, and the same thing becomes alkyl substitution when it is outside, when it is not a part of the cyclic structure. It is present separately as an alkyl group. So, alkyl group or ring residue, it is an equivalent thing. Therefore, in the table we can see that for each of such things we add plus 5 to it. Then there is a third category, that is the double bonds which are present, they have a special position and it is termed as exocyclic double bond. So, what do we mean by exocyclic double bond? Let us see over here. In the structure, you may see that the 1,3-butadiene which is being formed, a double bond is present in the ring, outside the ring, and the ring, the double bond is perpendicular to the ring. This is the plane of the ring and the double bond is perpendicular to it. So, any place where the double bond is perpendicular to the ring, such double bond, and just immediately outside, touching the boundary, the border of the ring, and is perpendicular to the ring. There are two conditions. We can say that if I draw a ring separately over here, you may understand that this is a ring, this is a double bond over here, another double bond over here, there is a double bond over here. So, each double bond is in conjugation. This is the 1,3-butadiene base, double, single, double, single, double. So, this first bond and second bond, it is part of the base value, but this third bond, it is actually the extension of conjugation which I have told you earlier. And there is one more condition with this, that this double bond is perpendicular to the ring. It can be another condition. Let me just clear it. A condition may be like this. If this is a ring, benzene, we are making two rings, and in this ring, if this is the condition, here this is your 1,3-butadiene, bond number 1, bond number 2 and bond number 3. But in structure A and in structure B that I have drawn, in structure A, the third bond, this is termed as exocyclic bond because it is perpendicular to the ring, whereas in structure B, the third bond, this is not exocyclic because it is not perpendicular to the ring, it is parallel to the ring. So, this is the condition of an exocyclic double bond. So, we have seen three increments: the presence of extra conjugated double bond, the presence of alkyl radicals or alkyl substitutes and ring residues, and the presence of an exocyclic double bond. So, each of these additions for extended conjugation, ring residue and exocyclic double bond are added to the respective base value, and by finally adding these values, we can predict the mathematical or the calculated value of maximum wavelength for a given organic molecule. Let us do some exercises. Here also you can see I have specifically shown the exocyclic bonds in these diagrams. Here in diagram first, this is an exocyclic bond because it is perpendicular to the ring. In the second diagram also there are exocyclic bond. When we are referring to an exocyclic bond, we must remember, like we have denoted A and B to the two rings. So, for ring A, this is the exocyclic bond, but for ring B there is no exocyclic bond because the other bond is not directly attached to the ring. So, whichever bond is attached to a ring, it becomes exocyclic for that ring. Similarly, in the third diagram, you may see this bond number 1 is exocyclic to B and this bond number 2 is exocyclic to A, because bond number 2 is perpendicular to A and bond number 1 is perpendicular to B. So, here there are 2 exocyclic bonds. Similarly, in this case, in the fourth diagram also, you may see that a bond which is present in ring B, this bond is exocyclic to A and this bond is exocyclic to C as well. It is perpendicular to both the rings. So, simultaneously a single bond can act as exocyclic to 2 rings also, for whichever it is behaving in perpendicular to the respective ring. So, I hope you are clear with the presence of these conditions in the particular organic molecule. So, now we can practice it in these given molecules. Whenever we are calculating the Woodward-Fieser rule, using it and calculating the lambda max, we have to first write the base value or the parent value, whatever you call it. So, we know there are 2 base values. So, you must see, since it is a cyclic molecule, so what condition it is? Is it a homoannular or a heteroannular? I can see the double, single, double or the 1,3-butadiene that I am trying to find. I can make that, but using both the rings. That means it is a condition of heteroannular ring. This is the condition of heteroannular ring. So, let us go back and see what was the value for a cyclic diene of heteroannular condition. The value that we take is 214 nanometers. So, we will write the base value as 214 nanometers. Then after taking the base value, we will add increments to it. And what are the different increments that we can add? The different increments that we can add are, first is extended conjugation. Then second that we are supposed to add is exocyclic double bond. And the third we are supposed to add is alkyl substitutions, or which is also termed as ring residue. We have to use the term ring residue in case of cyclic structures. So, can you see any extended conjugation in this molecule? No, there is only 2 double bonds which are in conjugation, which is part of the base value. That means nothing has to be added in this place. No, it is 0 over here. It is 0. So, actually you cannot, you can omit it also, but as I am explaining, I am writing it step by step. The next is exocyclic double bond. Is there any exocyclic double bond in the molecule? Let us see. I will rub this thing and now we must see there are 2 bonds. First we will refer to these rings as A and B. Let us see for ring A. Is there any bond which is perpendicular to ring A? No, there is a bond, but it is away at a distance away from it. So, it is not exocyclic. Now, let us see for ring B. Is there any bond which is perpendicular? Yes, this bond which is present over here, it is perpendicular to ring B. It is perpendicular to ring B. So, this is exocyclic for ring B. So, there is one exocyclic bond, and if you want to refer to the table, you may see that for each exocyclic there is a value plus 5, and for each alkyl substitute or ring residue also we will be adding a value of 5. So, for exocyclic we will write plus 5 Nm, and now we have to see the alkyl substitutions or the ring residue. So, we will only see in the place up till where our conjugation is going, not beyond that. I will rub this extra things so that we may understand. Our conjugation is moving from here. So, this part here we break, we can break it over here, this and this. These 4 places where already numbers are mentioned, 1, 2, 3 and 4. These are the 4 places where some alkyl group or the carbon atoms are present at the terminus and are acting as ring residues. So, the position 1, 2 and 3, these are part of the ring. So, they are termed as ring residue, and this is a pure alkyl substitution. So, it is only the difference in the name, the values remain the same. So, ring residues and alkyl substitution are total 4, and for each we have to add 5. So, 5 multiplied by 4, that is equal to 20 Nm. So, finally, we have to add these values. 214, we will write it here clearly, 214, 20 and 5, and when we add it, it makes 239 nanometers. And what is this 239? 239 Nm that we have calculated. This is the value of lambda max for the given molecule. In this way, by applying the rule, we have calculated the lambda max for a molecule. We can take one more example. The base value, first we will write the base value, then we have to write extended conjugation, extended conjugation, we have to write exocyclic bond, and we have to write ring residue or alkyl substitutions. Quickly we will see. Now, this is an example of homoannular ring. The base is present, the 1,3-butadiene is present in only one ring. So, for homoannular ring, the base value was 253 nanometers. So, we will write it over here as 253 nanometers. Here also there is no extended conjugation. So, we will omit it. Exocyclic bond, is there any exocyclic bond? Let me write. First we should always mark the rings A, B, C, since there are 3 rings over here. So, is there any exocyclic for ring A? Yes, this bond is exocyclic for ring A. For ring C, yes, this bond is exocyclic, but there is no exocyclic for ring B. So, there are 2 exocyclic bonds for we can specify it for A and C, and for each exocyclic how much you are supposed to add? You are supposed to add 5. So, we will write 2 multiply by 5. Then we have to identify the ring residues over here, similarly as we did in the earlier one. Let us see only from where the conjugation is starting, nowhere else. So, here 1, 2, because the conjugation is up till here. So, from where it is starting and where it is ending, this is one part, this is one part which has a carbon to it at both the ends. Then there is no alkyl group over here. Then at this terminus you can see a line going here, here also is a carbon, and a line going here, here also is a carbon. That means 3 and 4. There are 4 ring residues, no alkyl substitute, all are ring residues, all are part of the ring. So, again for each ring residue we add a 5. So 4 multiply 5. So it will become, this is 20 and this is 10, and our answer comes out to be 253 plus 10 and a 20, that is 283 nanometers. And what is this? This we have calculated as lambda max. It is written as lambda, the symbol of lambda, which is used for wavelength, with max as underscore, is the maximum wavelength for the given molecule. And in this way you can calculate the lambda max for n number of molecules. I hope you must have understood this topic of Woodward-Fieser rule for dienes and polyenes. In the next video, we will be discussing about the Woodward-Fieser rule for another category of molecule, that is alpha beta unsaturated carbonyl compounds. Thank you.